Thank you all for coming. Thank you all for being here. Welcome to the talk, Scaling SparkR in Production, Lessons from the Field. That's the title of the talk. You'll find there's going to be a little bit of overlap with Felix's talk from before, but I've also sort of a different focus, which means there are going to be a number of other things, other aspects that we can add to this discussion and hopefully will be useful to you. Very quick introduction about myself. My name is Heiko Korndorf. I'm from Europe, which you probably can tell. I'm the CEO and founder of Wireframe, a startup company based in Europe. I'm a data engineer, what you call it nowadays. I graduated in computer science. One thing that's maybe specific to me in that sense is being from Europe. I've worked mostly in non-web companies, in manufacturing, in bricks and mortar, so to speak, industries, which brings a slightly different set of challenges with it. And also, obviously, which is for you probably not a new insight, is in Europe we're lagging somewhat behind the US in terms of innovation and adoption of new technologies. Yeah, we're, as I said, small startup. When we have launched a product now, a rapid application development environment for Hadoop and Spark. We're going to launch a product which is in the category of data science as a service in Q2, which is based on Spark and R, which brings us to the topic of this talk. Before continuing, a quick show of hands. Who in the audience is a data scientist and an R user and familiar with? Okay, cool. And who would be a data engineer, Spark expert, working with? Okay, so whoa, that's the minority. Okay, very interesting. But which is good because coming from the Spark side of things, from the data engineering side of things, I hope there'll be a number of insights I can share with you if you're a data scientist. If you're a data engineer, hopefully there are also things you can learn from this talk. So what's the agenda? We're going to briefly talk about SparkR, the architecture. That's slightly overlapping with Felix's talk, but nevertheless I might give it a slightly different perspective on that. And then we're going to talk about projects in Europe that we've done. Started 1.5 years ago, almost 2 years ago. So we work, in terms of SparkR, actually, in terms of adoption of SparkR, we're quite advanced in that sense. We've been with SparkR since the beginning, actually. And I'll take those projects and demonstrate the challenge that we had with this and how we solved them with SparkR and what our results have been. One key aspect is, what we're going to talk about is what we solved with Spark 1.5 and 1.x. That was roughly a year ago. That was our first stab at the problem we took with SparkR. In particular, how we parallelized the problem at hand and what the results were. I'll talk about briefly some pedestrian problems, which are not deep conceptual problems, but still in a real-life project might make life slightly difficult for you and make it a bit more challenging. Then in summer of last year, we moved on to SparkR based on Spark 2.x, 2.0 in that case. And that brought in new features, in particular with parallelization and UEFs. We're going to talk about that then later on as well. And coupled with that, we're going to talk about the cloud, which is not unique to Spark, but of course goes hand in hand. And in particular to our problems, to our clients that we're going to talk about, cloud was another key driver of the results we achieved. And we're going to go into more detail later on. And then probably the last third of the talk is slightly technical, but more non-technical in a sense. We found that integrating data engineering and data science was, how can I phrase this, was sort of, initially it looked like a very peculiar situation, but then we've seen it again and again actually now in 5 or 6 projects that we've done, which felt like there was a pattern to this. And I'm going to talk about this pattern of integrating data science and engineering, which I think is quite helpful to maybe make this explicit and reflect and have a think about this. And I'll end with a broader look at the ecosystem and an outlook from our perspective, what are the next steps and what we plan to do in the future. So R, not much of an introduction needed for you because obviously many people in the audience are R experts. That was not true for us, coming from the data engineering perspective. Basically what we knew is that R existed, but that was more or less all I knew 1.5, almost 2 years ago when I downloaded R for the first time and got my feet wet. It's a very popular language, which I discovered then. There's a large ecosystem behind it. It was designed by statisticians. In one talk I've heard that's one of the big advantages of R, and it's also one of the big disadvantages of R, and I think this is, you can see this if you then drill deeper into R, that there's a number of good things about R, but equally some challenges because it was never thought to be a large platform that could scale, and there are things probably that haven't been built in from the beginning, but some things that can be now very, very well addressed with things like Spark. As I said, so the immediate pain point that everywhere pops up is R being designed as a single node, primarily a single node platform. Data has to fit in memory, and there is limited support for concurrency. So that's a challenge that we see everywhere we go. Everybody's very happy with R per se, but scalability is the major problem. So quick overview of the projects that we've been working on. There were 2 projects. One was source systems. On the left-hand side was a mainframe system, exporting data in CSV, moving on to the R system, to the R server, doing some time series forecasting there, writing results back, and then do some downstream processing on that. And the other project was Hadoop already in place, but then again, exporting file dumps to an R server, doing calculations, computations there. In that case, that was customer behavior analysis, and then feeding back again the results into the Hadoop cluster. Also, in the first, as mentioned, the first project, Hadoop and Spark were not yet in place, but there were plans to move to Hadoop later on, to plug the data into a data lake, and then from there on do the R processing. And in both cases, scalability was an issue, and the question was, how can we address this? What can we do about this? And we felt then like to suggest, let's give SparkR a try, and that's what we've done, and that was the beginning of our journey. So the initial view that we had was quite naive, to be very honest. It was, well, it's R running on Spark, so what we do is we load our R code in SparkR and execute it, and we're fine, we're done, we can go home. Not quite, obviously, not quite. So there's more to it than that. But in a naive way, that's how it looks as seen from R. If you start your SparkR shell, or your SparkR shell, or your R shell if you want, if you start your R shell, there are actually 2 lines of code. If the system is properly configured, 2 lines of code will suffice. You execute them, and your R shell is hooked up and connected to the Spark cluster in the sort of the back end, and is now tied into the Spark cluster world and gives you access to a number of great features. But still, that by itself won't do the trick. So if you dig deeper a bit, then into SparkR Architecture, this is now a slide I, of course, can relate to the data and engineering view, how that looks like. This is, I'm going to be a bit brief on this because Felix already mentioned this before. There's one addendum to this. We also what I have to mention as a disclaimer here is everything that in Europe we've seen so far is SparkR on Yarn / Hadoop. So that's another layer that comes into play here for us. So what does SparkR now give us if you look at it from a Hadoop Yarn and Spark context? Well, it gives you the option, number one, to execute R on the cluster as opposed to a single node where you have control. If you have a cluster with a number of computers, servers running, and if you want to start an R process, you have to sort of select a node and make sure that R runs on that node locally. And this is what SparkR does for you. That's the core feature if you want. The second feature is, of course, that by itself would be of limited benefit and usability, is data integration. What SparkR gives you is it allows you to move data back and forth between your R process and Spark, and also allows you to access Spark data frames from R, which means no more limitation in terms of data size. You can now have a data frame which is arbitrarily big, / has to fit in the cluster, which in most cases it should probably do fit in the cluster. And so with those two elements, you can do quite a number of things. I'm going to talk about this in a minute. The fourth bullet point on the slide that you see is it also opens up Spark APIs to the R developers, which is a great thing. Felix talked about this at length. Interesting enough, we're seeing, I wouldn't say resistance, but we're seeing some sort of skepticism. I'm going to talk about this also in a minute in more detail, why that might be the case. And the third bullet point is the new feature that SparkR brought now and was released with Spark 2.0, which is enhanced options for parallelizing your application with UDFs. So as I said, you can, if you have SparkR running, what you can do is you can use you can not only access Spark data frames from R, but you can also execute SQL against those data frames. And that's noteworthy because data scientists being proficient and fluent in R are doing fine. Scala is a different challenge for them, but SQL is something that virtually everybody, all data scientists are familiar with, and they're quite happy to adopt this. And it makes life easier for them. We're going to see in a minute also, because one of the usage patterns is that very much what we've seen in our half a dozen projects or so until now is that you have data coming in and you have to do some ETL, some data cleansing, validation, etc. What I didn't mention, by the way, both projects I showed in the beginning, both are comparable in size, and they're both consisting of around about 15,000 lines of R code. And being science code, they were not designed to grow and grow and grow. They've grown organically, which means now what we see in the situation, those 15,000 lines of code, when I talk to the scientists, they grudgingly admit that probably half of the code is ETL code, and they'd be more than happy to get rid of that code tomorrow because that would make their life so much easier. And that's a very good approach. It would be, in that case, for instance, to use Spark SQL. Makes it a lot easier. But we're going to talk about different options that you have as well in that context. And the other thing is what Felix talked about quite in depth. I'm going to just briefly mention this, is the native Spark ML machine learning APIs that you have at your disposal that you can use from SparkR. And they're great, and that's fantastic. And I mean, they are built from the ground up to take advantage of cluster resources, of concurrency and all these things. And that's just a snippet from the online documentation for Spark 2.1.0. So that's what you currently have available. And it's bound to grow, obviously, and that's all great. The reason I mention this with a slight sort of cautiously in a way is that being a data engineer, we introduced this and we presented this to the data scientists, and we thought, like, we're bringing them, this is your resolution to your problems. And we were met with slight degree of skepticism. And I think it was not because there was no technical discussion that this wouldn't be fit for purpose or they couldn't use this. My current understanding and my strong suspicion is this is due to the fact that the scientists have been using a set of R packages for a number of years maybe, and there's also this psychological effect here that you know your tools, and so they're not sort of, you have to convince them, and it's a process sort of you have to slowly gain confidence and have to tinker with it and see if it works, and then slowly maybe adopt this over time. It was not a situation where they would go like, oh, fantastic, we're going to just scrap all our existing R code and now use those APIs. They're all interested, but it's a process that I think will take some time. And I guess that what we'll end up with in the next 1 or 2 or 3 years is going to be some hybrid approach where we still have native R packages and native R code. And if it's fit for purpose, you're going to use those APIs. Very briefly, just touching on this, what was the other project, the first project I was mentioning, what was that doing? That was time series forecasting. Not going to go into any detail here much. The central idea is that you have this ordered sequence of data points over time. And we're using in that project R packages, using ARIMA, which is a method that was popular in the 90s maybe. We're not using neural networks here because we have too few data points. So ARIMA as a method is working nicely for that particular use case that we had. So a lot of, unsurprisingly for data scientists and machine learning, a lot of computation going on. You have to do a lot of computation to determine certain properties of your time series. Is it stationary? Does it have constant mean, constant variance over time, trending, seasonality, and you do a lot of parameter tuning and model selection. We're talking about several thousand models that we're evaluating in that project and for several hundred time series. So that already will give you an idea there's a lot of computation involved. Before we were able to address that pain point of running that time series analysis on SparkR, we had some pedestrian challenges. I have to just mention them. It's not noteworthy from a, as I said, conceptual, high-level point of view, but if you're in the trenches, if you're at a customer site and you have to make it work, it's just nuisances. And on the left-hand side was the problem. We were in the initial version running on an on-prem cluster, and R was not installed. And we can skip this discussion, but there was just no way of getting R installed in a reasonable time frame. So that sometimes these are limitations you have to live with. So what are we going to do? So what we did, and this is the nice thing about open source, obviously, we had to resort to some extreme measures, and we tweaked Spark and we tweaked R in a way that now we can dynamically deploy R and packages, which means running on a yarn cluster, what we've done is that we've just bundled R and all the packages up as dependencies that are dynamically distributed when you submit the SparkR job. So there was no need to even install R on all the cluster nodes. And that also solved the problem of the packages, because this was something we learned, obviously, that scientists love their packages, and it's all the engineers I talk to go like, yeah, give me the list of packages we're going to use in the next 12 months. And as you can imagine, that list varies on a daily basis, and they're swapping packages in and out based on the needs and new insights they generate. So that's something we resolved. The other thing is not a major issue. It was a small issue, but still noteworthy and maybe helpful to just be aware of is we found out that as a sort of a pattern in R, what very often happens is that people take data in, do some computation, processing, and write out the results. And equally, they would write out then some stuff like metadata, aggregated data, some KPIs, could be some graphic stuff, some PNGs, images plotting using R Markdown to produce HTML or PDF. And we were not quite sure what's the best way how to handle that. And the easiest way was then simply to write it back, to have each node produce that output and write it back, the binary output back to the distributed storage in the file system. That was the way to do it. There was some discussions, is that the right way to do it all? Because as an engineer, you would say you produce the output and then you do some aggregation, visualization later on when you have the results in persistent storage again. That's not how exactly the scientists have been working with this. They love to produce on the fly during their production run that data. So then, when we then finally had those things resolved, what that we have done is we took, and this is the very naive brute force approach, we've advanced since, but that was, I'm showing this because it shows you actually how much you can achieve with modest means in a sense, is as I said, this is the slide February, March 2016, so a year ago approximately. And the problem that we said was R script, time series analysis, roughly 100 time series, sequential computation on a not so small server, more than 20 hours, and the scientists have then tweaked it with parallelization, and they came down to 4.5 hours, which was something they didn't like to do because they wanted to focus on the methods, obviously, and not really with this concurrency and parallelizing their script and giving all sorts of headaches they would like to avoid. So this is a situation we've been at, and what we've done is simply we've taken a naive client that would submit embarrassingly parallel each time series individually, but it worked nicely, and the result was giving us more confidence. What we then done was on SparkR 1.6, on a 25-node cluster with 4 cores, we've brought it down to roughly 10-12 minutes of runtime, and that resolved a number of problems. I made a couple of people very happy and inspired confidence that this might be the right way to proceed. And then 2 things happened. The on-prem situation, I wouldn't say became untenable, but it became more problematic, and then there was the shift to the cloud. And then in that particular situation, it was Azure that was chosen. And so we re-implemented what we just described on Microsoft R Server for Spark. And the reason was R Server for Spark was a bit ahead in timing with SparkR. They've released their version in May or June, I think, last year, with support for UDF. So that would then mean you can also distribute literally across the cluster, your computation, your R functionality, which would mean we could ditch our Yarn client that we had and indeed move the parallelization inside the cluster, have one driver that coordinates all those different computation. Did that on Microsoft R Server. That worked nicely. And then we moved back, and in the other projects, this is all we're using, since we're not using Azure, is to SparkR 2.x, which brought the same features to the sort of came up with the same features in August, I think it was. Again, what Felix just talked about, D-apply and G-apply, which would give you the option to move computation across the cluster and have your R function run on either a Spark partition in the D-apply case or on an arbitrary partition/group that you can specify by giving a grouping criteria. And this made this redundant usage for this Yarn client and simplified our overall architecture, and has been actually ever since been our standard approach. So that's all good. And what we've seen, as I said in the beginning, is briefly we've been part of this data science, data engineering interaction, and it was fun to see. It was a great experience. And but it proved to be somewhat of a pattern. We've seen this in a number of places actually now, that you have engineering being used to, sort of repeatability and stability and performance and efficiency would be the key focus. And data scientists would be more like exploratory and loosely structured and have test tubes and shake test tubes, and sometimes things will blow up. And it's not necessarily such a sequential process as engineering. And I found this just recently in a talk from the Fields Medal winning mathematician, Cédric Villani, on a talk he's given, that the public perception of science would be that it's a slightly messy process. You start with something and then you go back and have questions and throw it again away, and then at the end you arrive at your result. And I think the data science process, I would call it, works similarly. But Cédric Villani said, and he knows a thing or two about science, obviously, being one of the leading mathematicians, said it's not quite correct. The real science process looks more like this. So it's a bit more messy, a bit more convoluted, it goes in circles. And he was keen to point out, which is very important, I think, the result obviously should be clean and elegant and structured and systematic. But the process how to get there is not so much so. And this has implications, and I think that's why SparkR is a great approach, is what we found initially, to be very honest, we found that we thought initially, SparkR felt to us 1.5 years ago more like a Band-Aid. It's, you have Spark and you have R, and out of necessity, you just glue them together somehow and make it work, and that's it, fine. But actually what we're seeing now is, there's another, I'm connecting this to another little story, which is, what we're also seeing in Europe is sometimes the approach that people take, which would be have data scientists develop the methods, and then re-implement everything on a pure native cluster environment. I keep hearing that not over and over, but I keep hearing that once in a while. But my impression so far is it doesn't really work. It's quite costly. It slows you down, and it's absolutely not efficient. So from that point of view, SparkR is again a great approach actually. And what we've seen is that you have on the left-hand side the development environment. People would use their IDE. Very often what we're seeing is RStudio is their IDE of choice for data scientists. They feel at home with this. They feel it's very convenient to them. And they would develop, but they would plug into the Spark cluster, so using data that resides in shared storage, using UDFs in SparkR, etc. And then they would check in their R function in Git or any repo of your choice. And the data engineers would take that functionality, download it or clone it, and integrate it into their production pipeline. It could be Hue, it could be Uzi, it could be, you name it, your tool of choice. But I think the key takeaway here would be, and I think that sums it up quite nicely, SparkR looks and feels like R to data scientists, and it looks and feels like Spark to data engineers. So in that sense, it is really bridging those two worlds quite nicely, and we feel it's, we've abandoned our perception that it would be a Band-Aid. We think it's actually a great approach and promises to be, yeah, very beneficial. So time is running short. Just to quickly say what we're looking at now is how to further parallelization. And there's two approaches. One would be this, if you have truly embarrassingly parallel problems, you could use this approach to have something outside the cluster that parallelizes work packages, starts Spark jobs, which in turn use UDFs to parallelize a second level. And the potential third level would be GPUs. That depends very much on the nature of the problem at hand, if that's a suitable approach. But that's basically what we're currently looking at for various use cases, how we could use such approaches. And other aspects are, we've talked about SparkR and data engineers and data scientists. We've seen now use cases where a slightly tighter integration might make sense. One would be that we have a single Spark job that does some stuff in Scala, ETL, and then finally calls R code, R functions, which is some scientific stuff. If you don't have the need to persist your output in between, you would end up with one single Spark application that consists of Scala bits and R bits. That doesn't work out of the box currently, and we're tweaking Spark, which is not what we actually want to do, but it's necessary to get it running, and maybe this is something that would be interesting for the Spark community wider. So I'm going to talk to the people like Felix and so on to see if there would be broader demand for such a feature. And the other use case would be you have your R code, and as I said, you're fine with it, and basically all works, but you have one pain point, one particular method that doesn't really perform well in native R. So what you could do is you could rewrite that individual function in Scala natively for cluster optimization, and then wrap that in an R function call and expose it to the data scientists as a regular R function that they wouldn't see any difference for them, and it would still be Scala running underneath. So those would be sort of tighter integration points you could potentially have with the Spark, the Scala guys, data engineers, and the data scientists. At the very end, quick look, as Felix already said before, dynamic ecosystem. So we're seeing basically, we're seeing SparkR, which I just talked about. We've also worked with R server for Spark from Microsoft. And there's a new contender, there's a new framework available from the guys from RStudio, which is called SparkR. I think the next talk is going to be given by Nathan, the CTO from RStudio, and I'm sure he's going to talk about that. There's stuff like SystemML, FastR. These are particular projects, not not comparable to SparkR, R server, and Spark layer, but they could potentially be interesting for very specific use cases. And for us, the next steps will be actually just no revolution in a sense, but just continuation of the journey we've been on, like deepening the integration between data engineering and data science, bring more of an engineering approach to the data science team with source code control, continuous build, test management, etc. Scientists basically, they're very well aware that these are problems. They're very eager to address them. They don't have the same history as the engineers with those topics, so they're quite eager to sort of get into that. And yeah, and technical, the same thing applies. Trying to exploit cluster resources, increase performance, look at new approaches, and we're quite excited to be part of that journey, which will bring me to my end of my talk. And I thank you very much for your attention. And I'm not sure if we have time.
Yeah, great talk. Really enjoyed that one. I think that we're just bumping up against time. We can have time for one quick question, and then, yeah, I mean, you can stand outside the door and answer others.
I'm available.
Hi, Heiko. Great talk. This is Ravi Kaushik from American Express. Just wanted to understand there are multiple efforts from Microsoft to get the R into Spark and distribute it. There is R server and now SparkR. My concern is which of the algorithms can be easily distributed and make it efficient and accurate in terms of performance? And are they the same
I'm not sure if I see two strands of your question. One is R server, Microsoft R server, and SparkR.
Correct.
That relate, and then you say how can you distribute algorithms and parallelize them efficiently?
Correct. Is there a concerted effort to get to both of them? Well,
it's a good question you're asking. Very, very good question. There was to be very honest, there was no master plan in the beginning. It was, as you can imagine, there was projects and deadlines and budget and blah blah blah, all these things. So we were just running and trying to make things work. And then we ended up to move to Azure because that was the client's preference, and the APIs were already there and it all worked nicely. So what happens now, what we currently is that we're actually at the point where we caution the client because there is now a risk that you would, if you just without any further consideration, just continue down that path, there would be some lock-in into the Microsoft APIs. And that might be not a bad thing if you do it consciously, if you want to do it deliberately because there is you have thought it through, then that's perfectly fine. But if not, then there's maybe not, this is not the best strategy. So what we're currently looking at is, because the APIs are at this stage quite similar, Microsoft R Server API and SparkR API, and we're not using any particular things that would be. So we have a common denominator, and we're looking at currently to build a little abstraction layer that would allow you to use the same parallelization logic, because conceptually it's the same. You have a driver, you have UDFs, that would then allow you to basically plug in different runtimes, i.e. Microsoft R Server and SparkR if you wanted to. If this, and now you have Spark layer coming into play as well. I'm not quite sure. My view is if they're going to remain similar, then such an abstraction layer might be a good idea. And if they develop into different niches, that they address different use cases, that you wouldn't have a common denominator anymore, then it's anyway fine in a way, again, because then you would probably use framework X, because that would address your pain point in the best possible way.
Cool, great. Let's give them another hand and we'll prepare for the next stop.
Thank you.